theory, say, and just looking at non-uniformal vacuum with the Coulomb branch, the next simplest thing would be to perturb the theory a little bit to add some relevant operators in Hamiltonian density of the CFT, and I'll suppose here to be irrelevant, delta less than D. If it's irrelevant, it does nothing at low energy. It blows up into UV, and you don't really have a theory anymore in general. Actually, the case delta equals D is interesting, but there's only so much time, so I'll just put a few references in notes. Anyway, with delta less than D, this is something which becomes effectively larger as you flow to lower energies, and so it's changed the low energy physics. And we know how to study this in the dual theory and gravity theory, because adding this to the Hamiltonian is just what we've been doing to make it generating functional. And we can think of generating functional as just being a way to generate the correlate of the original theory, but it's equally well a quantum field theory in its own right. So with the sign convention I was using, this is taking that J of X I was coupling to the operator and just setting it to some finite constant value. I know that again is a sign convention here. So we now have some perturbation of the boundary conditions, and remember, this means turning on a non-zero value for the previously fixed mode. So the bulk field goes as Z to the D minus delta, which is just right. When delta is less than D, this grows as we move away from the boundary towards lower energy, exactly like, of course, the corresponding operator. And then we have to figure out what happens when the perturbation becomes large, at large Z, low energy, things become nonlinear, and then we have to figure out what happens next. And it's actually, when we're in N equals 4 theory, there's a nice example, a rich example, that I'll describe, which is to add a superpotential masses for 1, 2, or 3 of those N equals 1 superfields. So 1, 2, or 3 non-zero. And this is going to have to be fairly descriptive, and this section of the written notes will be heavy on references. This is more a guide to what people have done than all the details. But I'll tell you what, for one non-zero mass, it's believed to flow to a new fixed point. A new strongly interacting fixed point. For two masses, it's believed to flow. For two masses, what's left, the massless part, is just the N equals 2 gauge theory, which is just the subject of Seiberg-Witten. It's believed to flow to an SUN version of Seiberg-Witten. Which in particular means that the massless sector is a U1, is non-interacting. And the massless sector is just a U1 subgroup of the original boundary symmetry, which means it is non-interacting. With three masses, the massless sector, the chiral superfields are all mapped out. What's left is the N equals 1 gauge field, and that's believed to be a confining theory, and so with three masses it's confined. So there's expectations from various kinds of field theory reasoning, and it's interesting to see the way the geometry reflects all of these. So that's up. Oh, that's within that. That's the central point within that space. Oh, I'm sorry, you're right. Yes, sorry. Actually, I forgot that. Let me come back to that. That's a really good point. So let's see the way that the geometry reflects all of these. So now I mentioned for a while back what the dictionary was. These operators, they correspond to this free-form fluxes on the 5-sphere, and the 5-sphere has no free cycle, so these are not, typological, not monopole, different type, dipole free-form fluxes. And the supergravity folks have a trick for studying these called consistent truncation, where they write down an effective 5-dimensional theory for this mode, and then solve it. And it's really magic, because there's no symmetry that would prevent this. There are the bigger mode here, some harmonic on the sphere, it's not lower in energy than the other harmonic by a lot. Symmetry doesn't keep predicting with them, but there's some supergravity magic where they can write down 5-dimensional Lagrangian, solve it, and then lift it with a 10-dimensional solution, and it can be applied to this case. And so first, for the case of one mass of flavor, when they do it, they get a 5-dimensional potential that looks like something like this, where the N equals 5, so this is the potential for this mode. The N equals 4 theory that we've been dealing with is up here, which seems kind of unnerving, but as we discussed, this mode has negative mass squared, but if it's not too negative, then the boundary conditions stabilize the system, a la Bright-Lohner Friedman, and it's okay to have the super. We know we're in this situation because if you go back to the the M squared equals delta minus D dictionary, being relevant, that is delta less than D, exactly means being tachyonic in the supergravity, and you kind of guess what happens. There's some solution where the field rolls, so here's the value at the boundary, here's the value at the horizon, and there's some solution which has here's Z equals 0, Here's Z equals infinity. Here's ADS region. There's some transition region as you roll down the potential, and then there's a new ADS solution. So this is a particular. This is exactly what the field theory reasoning leads us to believe, that you flow from one strong coupling theory to a new strong coupling theory. You can match up the details of what you expect. Yes. Unstability is equal to. Unstability is equal to. This is instability. The diagram is satisfied here, meaning that there is no instability. Tom talked about this too. There is no instability in time, but there's in some sense, but there's not really instability. But you don't roll down a thing in time because the gradient energy protects you. But you can roll down when you travel in space in the radial direction. That's what you're doing. Sorry. The final descent. If you see a potential like this, you don't expect this to be stable. This solution. That's what I'm saying. And I'm saying that it is stable because I'm not sure if maybe I'm putting this in question, but I'm saying it's stable because there's also gradient. There's also gradient energy that if you look at time evolution, actually, turns the potential up. In zero gravity theory, you have this is the potential in the gravity theory. Sorry, this is the potential in the gravity theory, and when you look at the radial equation, there are solutions which start here and end up here. Now, with two masses, you can do the same thing, and there's some other direction in the potential that you're flowing in, and this one's different because you end up flowing sort of out to infinity in field space. The two masses, the same strategy, when you lift it to a 10-dimensional solution, gives you a singular solution. So this is with one mass. It does what you expect. Two masses gives you a singular 10D solution. But it doesn't have a band singularity because then you look at it carefully, you realize that it's just a bunch of D3 branes. And so what the geometry is here is that, well, let me draw ADS space, conquer ADS space. This way, this is Z equals 0, the boundary, and the spatial things are shrinking up. And it never gets to Z equals 0. It's kind of a bad way to draw the picture. But the point is that the whole space, the point is that you never get to Z equals infinity. The geometry smoothly rounds off. This is actually the contact direction here. And this is Z equals 0, and they smoothly round off at some Z equals Z max. In terms of the metric, you have this ds squared is L squared over G squared, and U dx2. And again, in the ADS geometry, one has arbitrary low energy excitations by moving the excitation to smaller and smaller Z. That reduces its energy in terms of the gauge theory as much as you want. But once you cap off the geometry, you can't do that, and so you have a mass gap. So whenever you're trying to perturbate a relative perturbation to a conformal theory, there's a good chance that all you're going to do is give mass to everything, and on the geometric side, that's reflected by capping off the geometry. Here, though, it works out that you've got this plus you have n minus 1 D3 branes, not D3 branes, sorry. There's the minus 1 distraction, we won't talk about that either. And so the bulk theory exhibits exactly the massless sector that you would expect from the field theory. And the thing about Seiberg witness is the whole moduli space. These D3 branes actually have lots of places that they can sit. And it's true that when you bring them together in certain ways, you do get, as Tom reminded me, interacting fixed points. Actually, you would expect then on the gravity side to get some interesting geometry as you reach those points. And I remember thinking of it years ago, never turning. You know if anybody ever turned that out? Palmer problem. Yeah, it's a great question. I mean, So I guess part of the problem is that the supergravity folks first have to tell us what the metric is for arbitrary distributions of D3 branes, because this trick gives you special distributions. If they would tell us what it was for arbitrary distributions, then we could bring it to the artist and find out what is the geometry. Geometric nature of this is very smart. You have some examples that have this distributed for large animals. We don't really understand where you're starting from. Okay, right. Right. You said we understand that on for small that word, where it might not be in the geometric regime. Good. Okay, with three masses, you try again the same trick. That is, you get some potential, you follow it off. 5-dimensional solution, you get lifts to a singular 10-dimensional solution. Question? Yes. A good question. This consistent truncation magic chooses a particular point in the moduli space. And of course, in fact, of course, when the moduli space, I mean, the consistent truncation is a solution generating effect that doesn't capture everything. And for a while, it was a goal to try to find the gravitational description of the general point on the moduli space. But it seems to be beyond the supergravity discussion. You don't have to be there, but that's described explicitly that reaction of the D3 grains. It seems like a question. Of course, the people who've done the most of it are close to order. And they pushed out the problem, made some progress, but I don't think they ever gave a general solution. It's not smooth when the fields run up to infinity. It's unique that it's a recipe. They look at the recipe equation, and it's a trick. And it's a trick which it certainly is one-to-one in the way it's used now. Yes. So in fact, let me tell you, when you have three masses, this becomes even starker because, let me see what happens with three masses. With three masses, you can do the same thing, the five-dimensional thing flows off, you get a single 10-dimensional solution, but it's not any recognizable simple brain. No, this is in 2B, so there's no 11D left. Yeah, well, again, the two-mass singularity really is just D3 brains. Let me finish to tell you what happens with three masses. So with three masses, if you're Max Strassler, you look at the gauge theory side of the duality for inspiration. If your superpotential is W is ML, then the moment is equal, say, phi alpha squared plus 1 alpha beta gamma commutator of phi alpha and phi beta gamma is all traced. And I'm leaving off the constants. Then the F-term equations tell you that, again, I'm leaving off the constants, m phi alpha is epsilon alpha beta gamma, commutator of phi beta and phi gamma, which is to say that you have vacua for any, so again, these are n by n matrices, and you have vacua for, so there is one vacuum for each n-dimensional representation of SU2, then it doesn't have to be reducible. So there's a huge number of vacua, including the trivial one, phi equals 0, and phi equals 0 actually is the confining one, and the other ones have various sort of mixed confining Coulomb behavior. Remember that the scalar parts of these superfields arose as the coordinates of the D3 brane, and this is saying that those coordinates are becoming non-commutative, which comes back to the question from the last lecture, because Rob Myers explained that when you put D3 branes in a transverse flux, it becomes energetically favorable for their coordinates to become non-muting, and they pop out in two directions to become D5s. And so the correct behavior of the supergravity with three masses is it ends on, it actually ends on a D5, or an S5, or in fact, sums of many 5 branes. And the fact that there are many ways to calculate the geometry reflects the fact that the theory has many vacua. And so there's a nice match between, you notice the several things, there's a nice match between field theory expectation and what the gravity tells you, but also it takes some trial and error in many cases to figure out where the geometry flows to. It's not always obvious. The perturbation gets big, and it's not obvious what the geometry then does, and in particular, it's useful to have insight from the gauge theory as well. By the way, you can once one does this, one can go back and figure out what the consistent truncation was doing, and it was trying its best. It was producing some smeared version of the D5 brane. It was smearing this to the 5-dimensional object out into like the 6 or 7-dimensional object, and so it was trying very hard to get the right answer. The last thing I want to say about, I'm pretty much on schedule. The last thing I want to say about this is, I told you that one of these theories confines, and I want to tell you how to see that. So, one observer I didn't talk about is to measure the potential between a source of forming an antiquark fundamental that maps to the QQ-bar potential. Fundamental. There are fundamental, you can always get fundamental sources. So here is your boundary, and it corresponds. So the string, if you think about it, in going back to Truss and Wilson, is thought to be the color electric flux tube. And one could say more to justify this, but time is short. The way you calculate potential is to consider a string hanging down to the boundary, and then subject to suitable renormalizations, the potential is just the tension of that string. The total energy of that string having its tension. Now, the tension, the effective tension, so again, this is the z direction, is the local tension times the translation, the gravitational relation, the translation from local inertial coordinates to the global coordinates. And so the further it hangs down, the less its energy, the further z it hangs. And exactly in ADS phase, as you must get, because just by its scaling variance as a unit, as you pull the end further apart, the string hangs down lower, and so it can reduce energy and in such a way that the potential goes 1 over r, much by symmetry. The coefficient is interesting, but no time for that. In a confining vacuum, on the other hand, we have encountered this idea that there is some Zmax. And so, the draw is a bit larger. The string hangs down, but it can only hang down as far as the space lets it, and then you pull the end further and further apart, and most of this thing is just running along the bottom of the space at the largest value of z, the infrared value of z you can get, and so the effective tau of the string is just zero. It confines. And that's what happens with free masses. With two masses, the Southerhood nebula are not confining, they're cool-orbit, but for a different reason than over here. There is a floor to the space, as I was saying, for n equals 2, for the two masses, but there's also the d3 branes. And so now I'm going to draw the same picture. So here's z equals 0, where the string hangs down from. Here's the floor, and now I'm looking from a different perspective so I can see, those d3 branes. So I'm looking now from a perspective that sees the three directions more explicitly, and so here's your d3 branes sitting at the bottom of the space, and the strings hang down. So once the string ends on the d3 brane, it doesn't go, it starts in flux. But the flux is just the U1gh field and it's free to spread within the d3 brane. So you get a Coulomb potential for a different reason than you did in the AES phase when it's still Coulomb. So the general thing, d3 particularly, when a lower dimensional object dissolves in a higher dimensional, ends on a higher dimensional, it doesn't just end. There's always some, the arrow's running the other way, I guess. There's always some flux carried by these objects which has to somehow run through the higher dimensional object. But again, because the three branes have a really gauge field, flux is going through. Okay, so that's the general idea of RG flows and also some specifics. Yes. You've got strings, you have D strings, and you have DQ bound strings. So you have the entire SLM object. So in fact, with all of these things, you also want to ask about the magnetic stages of the magnetic, magnetic objects. Are they combined? Are they cold mechanisms? There's always an analogous story for those. And similarly, you can ask for external stories. CFTs have operators in the range between the minimum allowed by unitarity electrical algebra and half the dimension of the CFT. And this is the regime where, as we said, you have to take the alternative boundary condition equals the less obvious one, the scalar field at z equals 0. But this is also special for another reason. It's special because the delta is less than z. Less than z. And so the double trace operator squaring the original operator is relevant. Now, again, I'm using here large n factorization. In the large n limit, the amplitude, they have some operators at a point, and they're each connected to the rest of the graph, but the leading in n amplitudes are fully disconnected between the two operators, and so the dimension at this point, the original dimension. And so we want to see